Tyler here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
This example we'll see what we can tell about spacecraft trajectory or orbit based solely on the gravitational potential energy and its kinetic energy. We have the following scenario. 10 days after its launch, the Mars Climate Orbiter was 2.87 million kilometers from the Earth and traveling at that's 12,000 kilometers per hour relative to Earth. A. At this time, what was the spacecraft kinetic energy relative to Earth? And B. Potential energy. So A, of course, half times mv squared. But let's see what is our velocity. So V is 1.2 times 10 to the 4 kilometers per hour. And if we divide that by 3 by 6, or 3.6, we get the speed in meters per second. And that is about 3.3 kilometers per second, or 3,333 meters per second. We need to use SI units here. So we get half times m. The mass of the spacecraft is 629 kg, triple G, times 3,333.3 meters per second squared. This is going to be a big number, so we get 3,494 times 10 to the 6 joules. Let's keep it in this format. And then B, the potential energy of the spacecraft Earth system. Essentially, the gravitational potential energy of the spacecraft in the gravitational field of the Earth. So we know the expression for that is it's minus always G times m, and then the mass of the central body Earth divided by distance. Be careful, not the square of the distance. That would be the gravitational force. We're talking about gravitational energy here. So we have only one R. And minus 6.67 times 10 to the minus 11 newtons per, that's Newton meter squared divided by kg squared. Mass 629 kilograms, and mass of the Earth we know to be 6 times 10 to the 24 kilograms divided by the distance. So that's 2.87 times 10 to the 6 kilometers, so 10 to the 9 meters. And that kg takes, or those kgs cancel the kgs here, meters go away, we have Newton meters, which is joules. Good, so we got the correct units, and the value is 87.7 times 10 to the 6 joules. Now, if we compare these two numbers, we say that, or we see that it has more kinetic energy than the negative potential energy, or in other words, it is able to completely nullify the gravitational potential energy of the Earth that will happen later in the orbit, but as it goes further away. But the key thing here is that the total energy, let's call it E, that is kinetic plus the potential, this is larger than 0, which means that this is, or the spacecraft is not bound to the gravitational pull of the Earth anymore. And that is, of course, what we expect from a spacecraft that is on its way to Mars and is mainly under the influence of gravitational pull from the Sun. And as it goes further into orbit, the rest of the kinetic energy, or part of it, will be taken away by the remainder of the gravitational potential energy, which is about minus or about 88 million joules. So this number will be reduced by 88 million, and what is left over, it will have forever. So it will definitely have some excess velocity as it keeps going, and that is in fact called the excessive hyperbolic velocity, and that comes from the fact that the spacecraft, when it left the Earth, it set out on a hyperbolic trajectory relative to Earth. Most likely it's still on an elliptic orbit around the Sun, but that is a different story.